Hello everyone, my name is Alexander Pierce and I'm in Physics 2211 at Georgia Tech. This is Lab 3 titled Black Hole. The purpose of this lab was to explore curving motion utilizing Newton's law of universal gravitation and Newton's second law. In part 1, Newton's second law was utilized to calculate the net force acting on a star orbiting a hypothetical black hole. This value was then plugged into the universal gravitation formula to solve for the average mass of the black hole, which came out to be 1.43 e to the 34 kilograms. In part 2, trial and error was used to determine the initial velocity that a spaceship must travel at to avoid getting sucked into the black hole or crashing into a planet. The initial velocity ended up being negative 2.95 e to the 7, 5.4 e to the 6, 0 meters per second. For part 1, it is assumed that the only force acting on the star is the gravitational force of the black hole. Therefore, Newton's universal law of gravitation was used to calculate the net force, and this value was used to update the position and velocity of the star. The parallel and perpendicular components of the net force were also determined. As you can see, you can manipulate the equation for net force in order to get two different components, a parallel and perpendicular component. These components add to give you the total net force. For part 2, Newton's universal law of gravitation was used to calculate the net forces acting on both the spaceship and the planet. These values were used to update the velocities and positions of the spaceship and the planet to determine their path of motion. By changing the initial velocity, I was able to alter the ship's trajectory. The fundamental principles used in this law were Newton's second law, Newton's universal law of gravitation, and the parallel and perpendicular components of net force. Let's start with part 1. The system is the star and the black hole is the source producing the force. The initial conditions are as follows. The seed of my email is used to determine the initial velocity. Here's the code I used for part 1. The initial and final velocities were generated from the seed email, and I used those values to calculate the initial and final momentum. I then found Fnet by dividing the change in momentum by change in time. To get Fnet parallel, I divided the magnitude of P final minus magnitude of P initial by delta T, and I multiplied by P hat. To get Fnet perpendicular, I subtracted Fnet parallel from Fnet. To get the mass of the black hole, I rearranged the gravitational equation to get the mass of the black hole equals the magnitude of Fnet times the magnitude of the position squared, divided by the gravitational constant times the mass of the star. I then found the average of those values to use in part 2. These three images show what my code looked like when it ran. The orange vector represents Fnet, and it's always pointing towards the black hole. That's because gravitational force is an attractive force. So the force by the black hole onto the star will always be pointing towards the black hole. The average of the black hole mass is equal to 1.434 e to the 34 kilograms, and it will be used for part 2. Fnet and its parallel and perpendicular components are the same in value to the rate of change of momentum and its parallel and perpendicular components. However, the rate of change of momentum can be directly calculated using the velocities and masses of objects that can be found from observations and measurements. Fnet cannot be measured or observed. You cannot find Fnet without calculating the rate of change of momentum. The value of Fnet is deduced, while dp dt can be directly calculated based on observations and measurements. Now for part 2. There are two different systems, the spaceship, which has the surroundings of the planet and the black hole, and the planet, which has the surroundings of the spaceship and the black hole. Here are the initial conditions. We use the average mass of the black hole from part 1, and the velocity needs to be found through trial and error. Here's the code that I wrote for part 2 of the experiment. I used the gravitational force equation to calculate the net force acting on the planet and the net force acting on the spaceship. To find the net force for the planet, I found the force acting on the planet from the black hole and from the ship, and I add those two together to get the net force. To find the net force of the spaceship, I found the force acting on the ship from the black hole and from the planet, and add those together as well. Then I used the position update formula and the velocity update formula to track the ship and the planet's motion in order to plot it when I ran the code. In order to achieve my mission of flying around the black hole without crashing into the planet or the black hole, I had to find a proper initial velocity through trial and error. My ship ended up traveling with an initial velocity of negative 2.95 e to the 7 meters per second in the x direction and 5.4 e to the 6 meters per second in the y direction. As you can see from the images of my run, my ship was able to successfully complete its mission. What initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? I had to find this initial velocity through more trial and error using the same code as before. I also had to ensure that my spaceship did not reach escape velocity so that it did not escape the gravitational force of the black hole. In order to orbit the black hole, I found that my spaceship should have an initial velocity of negative 1 e to the 6 meters per second in the x direction and 1 e to the 7 meters per second in the y direction. Here are some possible sources of error. In part 1, the average mass of the black hole is an estimated value, so it may not be an accurate representation of the actual mass of the black hole. In part 2, because the mass of the black hole is an estimate, it could have resulted in an inaccurate initial velocity used. Because the initial velocity was found through trial and error, it lost validity. Thank you for listening to my lab presentation.